This is just a little quick video on second order differential equations. And for this one, we're just going to assume that we're talking about characteristic equations with real values and not complex or imaginary values. So to start off with, we get the second order differential equation. This is just the general one. And one of the solutions that becomes apparent, since we're talking about y and y prime and y double prime, something that's really nice to take derivatives of is e to the x. In this case, though, I'm going to use t instead of x. So I'm going to make the assumption that e to the rt is one of our solutions. So I'm going to consider that my function solution. And if I take its derivative, I would get r e to the rt. And if I take a second derivative, it becomes r squared e to the rt. And we can substitute that back into this equation and see what happens. So if we substitute back into the equation, we get this, where y double prime becomes r squared e to the rt, y prime r e to the rt, and y is just e to the rt. And what's common between all three of these terms, of course, is this e to the rt. So I'm going to factor it out and see what happens then. If we factor out the ERT, then we're left with this nice quadratic on the inside based on r. And it's still equal to 0. Now the only way this is going to happen is if e to the rt is equal to 0, which can never happen as long as, well actually it can never happen, period. And then the only thing that's going to make this equal to 0 is this ar squared plus br plus c. This is called our characteristic. And this characteristic equation, this quadratic set equal to 0, is going to give us possible solutions, values of r, that we can plug back into the original here, this e to the rt part. Now, for this first part, we're going to assume that the r's are different real values. Later in this little video, we're going to see what happens when r starts repeating itself as a repeated root. And one of my next videos will deal with when r is imaginary and or complex. So let's do a quick little example. So here's a nice differential equation, y double prime minus 5y prime plus 6y is equal to 0. And it instantly changes into a characteristic equation by replacing the y's with r and the primes with powers. So it becomes r squared minus 5r plus 6 is equal to 0. You'll notice that's what happened back here. This is ar squared, and up here was ay double prime, plus br, by prime, plus c, and then we got the cy up there. So it's like it pops right out of the original equation. All right, to solve this, we can factor. Factors of 6 that add up to -5 are -2 and -3. Your factoring skills have to come back into play here. And we finally get solutions of r equals +2 and r equals +3. Now, two of the solutions, if we want to think of it, would be y1 is going to equal e to the 2t, and y sub 2 would equal e to the 3t. And these are both linearly independent solutions. And since they are, then we can kind of force superposition, I think it's called, on the final solution, and it would be the sum of these two may be off by a constant. So it would be c1 e to the 2t plus c2 e to the 3t. And that would be our general solution to this differential equation. Not that bad. So the trouble happens when we have repeated roots and then when we have complex imaginary roots. So let's see what happens when we have repeated solutions. So let's say we have this differential equation, and obviously I have it set up so that the characteristic equation is a perfect square. So that means we have a double root of -b over a. And we have to figure out what happens because we can't write e to the -b over at for both of our solutions because they're linearly dependent solutions. So we have to create a linearly independent solution. All right, so what we're going to do is we're going to find a function u of t. We're just going to generate some weird function u of t. I don't know what it is yet. And we're going to let y equal this ut e to the rt be the other solution when r is equal to negative b over a. All right, so if this is another solution, it has to work in the differential equation. So I'm going to go through and find first derivatives. So I'm going to take the derivative of u of t e to the rt, product rule, first times the derivative of the second plus the second times the derivative of the first. And then I'm just going to simplify it by pulling out e to the rt and reordering it so the differential is in front and the constant function is in the back end. And then I'm going to turn around and take the derivative of this one because, I want to plug in y double prime and y prime. So if I take another derivative, this would be the first function and this would be the second. So it would be first times the derivative of the second. That gives us this long piece right here. And then the second times the derivative of the first, that gives us this piece over here. And then reordering things, I get e to the rt u double prime 2ru prime, that comes from over here and over here. And then we have this r squared u of t. Well, the r squared u of t is right here. Multiply those two together. So just reordering it and getting the differentials in order. So that would be our second derivative. Now I just need to take these two pieces, the one in blue above and this piece here. So take these and the original one, which is right here, and plug them into our differential equation and see what happens. Now this gets a little messy and there's probably a better way of doing it, but this really shows you what's going on. Alright, so we're going to plug it into that equation. And when we do, here is the y double prime, here is the y prime, and here is the y. Now distributing, collecting like terms, and factoring out an e to the rt will get us to here. Oh, I haven't collected terms yet, I just factored out the e to the rt. And if we collect terms, we get something that looks like this. This piece here really turns out to be ar squared plus 2abr plus b squared, but I factored it out. And the reason being is I know that r is equal to negative b over a for this situation. And if this is true, then this piece is equal to 0. And 0 times u, of course, is going to be 0. Also, since ar plus b raised to the second power is equal to 0, then ar plus b raised to the first power is also equal to 0. That'll kill the first two terms here, or the last two terms. So what comes up to play is this one. We want this whole thing to equal 0. So this one also has to equal 0. But a can't equal 0 because we're dealing with a second order differential equation. So a squared definitely cannot equal 0. So if a squared is not equal to 0, that means u double prime has to equal 0. And there is only one function where the second derivative of it is automatically equal to 0. So u of t has to equal a linear equation, something like ax plus b. And that kind of gives us a hint on how to deal with the second root that we need to copy. So we take this linear function, and our y is now going to equal this ax plus b times e to the rt. In this case, negative b over a, but I'm just going to write it e to the rt. So introducing an x factor in front of e to the rt gives us our other solution. So technically, what this is supposed to look like is y equals, and usually they change the order of it. They put the linear, the constant term first, and then the linear factor second. So it generally gets written, the b turns into c1 e to the rt, plus, and then the a turns into c2 x e to the rt. So we get this linear factor involved. All right. Now, if we increase the degree, it increases another linear factor. Like if there's a triple root, you could imagine that we'd get ar plus b raised to the third, and then ar plus b raised to the second, then ar plus b, and they'd all equal 0, and you'd be left with u triple prime is equal to 0, and then you'd get ax squared plus bx plus c as your u function. So it's always going to be a polynomial. All right, so let's solve one real quick. Here we have y double prime minus 6y prime plus 9y is equal to 0. The characteristic would be r squared minus 6r plus 9 is equal to 0. This factors rather nicely into r minus 3 all squared is equal to 0. Therefore, we have a double root of r equals 3. Double. Therefore, the solution to this has to be, well, let's just say y of t. Y of t is equal to c1 e to that root t plus c2, and then you get this x factor e to the same root t. And that would be our general solution for this differential equation with a repeated root. Not too bad. It might get a little messy if we increase the degree. For instance, this one. This is y triple prime plus 3y prime, double prime plus 3y prime plus y is equal to 0. Now, the characteristic after, r cubed plus 3r squared plus 3r plus 1 actually factors into r plus 1 all cubed. It's one of those neat little math facts. So this means that r is equal to negative 1 is a triple root. It happens 3 times. And because it happens 3 times, our characteristic is going to have, or our solution is going to have a quadratic piece to it. So one way of writing it would be to say y of t is equal to, and then build it up. It's got a linear, it's got a constant, it's got a linear, and it's got a quadratic, x squared. And it's going to be multiplied by e to the root t. And then you could distribute the e to the negative t throughout, but this is a perfectly fine form too. All right, let's change it around a little bit. Say we have this equation. Now, the characteristic on this is, of course, r cubed minus r squared minus 8r plus 12 is equal to 0. And it doesn't factor very nicely. You'd have to use little synthetic division. The factors of 12 are 1, 2, 3, 4, and 12, 6 and 12. And the ones that work are positive 2 and negative 3. So if you want to do little synthetic division, you're going to find that 2 and negative 3 are the roots of this equation. But it doesn't tell you until you factor it if they're double roots or triple roots or whatnot. So I'm going to just give you a heads up that this is r minus 2 all squared times r plus 3. So we have 3 roots, except one of them is a double root. So we're going to get r equals 2, and I'll just say times 2 down there, and r equals negative 3, and that's just by himself. So this double root over here has to have a linear expansion to it. Well, that's what I'll call it. So we're going to get y of t is equal to, and I'll just write it in the linear form, c1 plus c2x, and then it would be e to the 2t from that double root, and then we have finally a c3 e to the negative 3t. So that's how you deal with real coefficients, real characteristic equation solutions. Even if they were square roots and whatnot, that'd be perfectly fine. The only thing that gets a little weird is when we start talking about imaginary and complex ones. So that's it for this one.